Hi, and welcome back, everyone, to part 15 of our Block 74 Apollo Guidance Computer series. Today, we're going to continue talking about memory within the Apollo Guidance Computer. We talked about sort of the S register a little bit in the last episode and talked about kind of the memory mapping scheme within the Apollo Guidance Computer. So we're going to dive a little bit deeper into that and start talking about the EBANK register or the erasable bank memory. As we talked about before, the Apollo Guidance Computer uses a mechanism of banking in order to allow it to access its full memory space for both fixed and erasable. And today we're going to talk about erasable. It's a little bit simpler than the fixed one, and we'll cover the fixed memory in our next episode. Now, if we look at our overall kind of layout of the Apollo Guidance Computer, we talked a bit about the S register, which is the 12-bit register that is used to address memory, and then later we'll actually cover the G register, which is the memory buffer. So that's the register that's actually used to transfer the data in and out of memory, and there's some parity that will associate with that. Well, we'll build the parity circuitry just to kind of keep historical authenticity, even though with modern memory, probably really don't need it, and we're not going to be flying it through the radiation belts or into out to the moon, so we won't have to worry about that radiation environment, which can cause some issues with memory. Anyway, back to the S register. So the S register is the 12-bit register that allows us to address and set our address for memory. Um, and as we talked about, well, 12 bits doesn't give us enough to address the entirety of the guidance computer's memory. So there's a series of basically bank registers that are used to allow us to kind of swap in and swap out parts of the memory in order for us to be able to access all the memory. So there's the erasable bank, which is what we're going to be talking about today. And then there's also the fixed bank and then the fixed extendable bank, or sometimes called the super bank. So one thing I will give another shout out to Mike Stewart, who provided me a little bit of additional insights around the extend bit that we talked about in the last episode. So the extend bit I thought was actually something that had been introduced as part of the Block 2 guidance computer. In fact, it was originally part of the Block 1, used a little bit differently, but it does allow you to kind of extend the instruction set, and it's important with kind of how instructions are ultimately encoded in the guidance computer. And we'll talk a lot more about that when we start covering the SQ or sequence register for instruction decoding. Anyway, so the EBANK register or the erasable bank. So it is a 3-bit register, so we can have up to 8 different erasable banks. And there's a number of control signals that are used to write data in and out of the EBANK. So first, there is the RBBK instruction, which basically reads the BB or both bank configuration into the write lines. So there is when we refer to the BB or both bank, that actually refers to both the EBANK register and the FBANK register combined. So the FBANK register is a 5-bit register that we'll talk about in the next episode. But whenever we see this BB or both bank, it's referring to both the contents, the 3-bit contents of the EBIT or EBANK register and the 5-bit contents of the FBANK register. So there's two commands. We talked about the RBBK. So this basically will read out the contents of both the FBANK and the EBANK register onto the write lines. And then there's also the U2BBK, which will write the contents, certain contents of the adder or the U register into the FBANK and EBANK registers. Now, there's also another way that data can be written into and out of the EBANK. Like many of the central registers that we talked about, there's a direct addressable mode, whereas the contents of those registers are basically used as if they are memory. So, we have both the XB3 or memory address octal 0003, which refers to the EBANK, And then there's also XB6, which refers to both banks, so the BB, which is octal 0006. And those are both write and read through the WSC and RSC control pulses. While I was doing research for this particular episode, I found this really great table which lays out all of those directly addressable registers and kind of how they work. So we've got 0000, which is the A register, 1 is the L register, 2 is the Q register, 3 is EBANK, we talked about. 4 is the F bank, which we'll talk about in the next episode. 5 is the Z bank, and then we have 6, which is the B bank, and then 7, which is not used, so that doesn't exist. And what's really helpful is this kind of mapping here shows how data is read into and out of those registers depending on what mode is being used. So we can see kind of here, well, we've got for the A, there's the right A pulse, and basically it's just kind of a straightforward, right lines in the contents. And then as we talked about in the episodes about the A and L registers, we have the WALS control pulse, which does a little bit of bit shifting. So this kind of is a good table, shows how that occurs. And then when we look at the EBANK, we can kind of see, oh, okay, we've got, which right lines are we bringing data into when we write, and then when we read it back out to the right lines, what right lines we're moving out. So this was very helpful because you'll notice that for the EBANK, when we write into the EBANK, we're actually pulling bits 9, 10, and 11 off the right lines in order to write into the EBANK. Whereas if we do the EBANK from both the both bank command, we're actually treating them as write lines 1, 2, and 3. And this is actually more similar to the RBBK and U2BBK, which uses bit positions 1 through 3 of the right lines or the adder in order for us to transfer data back and forth between the registers. So how does this look in the actual schematic that we're working on? So I'll just bring up the S register here. And if we'll start off, we've got the 12 bits. So I've got a series of 74 LS173. So these are both 4-bit registers. So we're going to use 3 of them in order to actually build the S register. And these are fairly simple. They bring in data off the first 12 bits of the write lines. And there's a WS control pulse, which allows us to write data in. So we use that as our enable. And because it's negative logic, we don't have to actually do anything. So it makes it quite nice. So if we have this is asserted, so it goes low, we'll enable our register so that it'll actually, on the right timer pulse, will load data into the S registers. And that will give us we've got a buffer here just so that we, again, keep our clock nice and strong, because we'll also use the right timer to write into the F bank and E bank registers as well. And then we also have our general reset that we'll use when we restart the computer and need to clear everything out. So that's pretty simple for the contents of the S register. Now, one thing that we have, I've kind of built 2 different kind of circuits that we'll be using as part of this, and I'll kind of show why. Is one is kind of this kind of control logic or decoder, which generates both the SACD, which is a control which basically prevents us when should we be scanning or reading into and out of memory. So this is useful because when we talked about those direct addressable registers, we're treating them as if they're memory. But what we don't want to do is that we don't actually write data in and out of memory whenever we're accessing those low bit memory addresses. So this kind of decoding logic, basically, we pull off everything on kind of, we got are lines 1, 2, 3, and 4. So basically the first 4 bits. And then we've got the rest. We're basically saying, hey, if we have any actually addresses here, we're basically reading an address at basically octal 0020 and above, which, because of some of the special registers and special addresses, we basically don't want to write to and from memory in that particular case. And then we'll also have some additional logic on our contents of 11 and 12 for, as we talked about in the last episode, for our erasable memory. We actually only use 10 bits. So the low 10 bits are used to address the memory, and then we use the banks to switch in and out. So these basically, by ignoring the contents of our S11 and S12 bit, we can actually generate a control pulse to say, are we accessing RAM or not? Because if we ever see data, if we ever see information in these 2 bits, we must be accessing fixed memory, because that memory doesn't exist in we only use the low 10 bits for the erasable memory. And this basically gives us, as we talked about the memory map, a signal to say, hey, if these are set, we're using fixed memory. If they're not set, then we're using erasable memory. So this is the fixed bank stuff we'll talk about in the next episode. One other thing that we've also created here is we need to be able to generate those control pulses or control signals to determine which of our direct addressable registers we're using. So we basically pull off our low 3 bits off the S register, and then we just run it through this basically 3 to 8 decoder, and that'll allow us to generate our XB0, XB1, XB2. This is actually our XB3 and 4, our XB5, XB6, and XB7. So these will actually go out onto our main bus because we use them as inputs for accessing the A register, the L register, and the Z register. So these are where we generate those particular signals from. And then in the case of the EBANK, FBANK, and both bank addresses, we'll actually keep them on the same board, so we don't have to use up any pins on the bus. So those kind of we'll just kind of write all the way down below. Okay, so let's start looking at the EBANK register. So again, we've got a 74LS173 4-bit register. And one of the things I'm still kind of playing around with is the boards that I've designed have space for 16 LEDs. So I've got the 12 that I'm going to be using for the S register, and I'm going to want the additional 8, so the 5 of the F bank and 3 of the E bank, that I'll want to be able to see which bank is being selected. So I'll have to figure out how I kind of shoehorn that into the 16. On the newer boards, I've got some additional space for some LEDs on the board itself. So I'll probably at least start off with the E bank, because those are going to be the ones that I really want to display, and then we'll see where we can show the F bank register contents. So in order to load the contents of the EBANK, there are basically 2 sources of data. One, we can get them from the write lines. So in this is the case of, we talked about the direct, if we use them as a directly addressable register, we'll basically pull that off of 9, 10, and 11. And we got that from that great table that I was able to find. And then we also have the scenario if we're loading data from the adder, we got it from the U01, U02, or U03 contents of the adder. And so basically depending on whether we've got the U2 BBK control pulse asserted, that'll allow us to select whether we load the data from the U register or whether we load it from the write lines. And then we've got the other logic here that we want to just decode is if it's a XB3 address, then we want to be able to access or write data into the EBANK register, or if it's the XB6 address, which is both banks, we'll also be able to wanting to write into the register. So that's kind of you can see the control logic that enables our register to load the data. This up here is kind of that similar logic for um, the EBANK register, which we'll talk about in our next episode. And so that's how we kind of get data into our EBANK register. Now, we also have a couple scenarios where we need to get data out of our EBANK register. And this is where we've created kind of the read logic in order to either bring it out through our BBK in sub or control pulse, or through RSC if we're going to use the direct accessible direct access into this register. So depending on which option, we then will read the contents out of the EBANK register, either onto, if it's an RBBK command pulse, we write it out on WL1, 2, and 3. But if it's a XB3, again, from that table, we want to write it out to the contents of 9, 10, and this actually should be 11 here. I will actually fix it while we are here. Yeah. So that allows us to kind of get the data into and out of our EBANK register. Now, the EBANK register is, again, it's not just register for storing data. It's actually the register which, in combination of the contents of our S register, so you can kind of see I've got this bus with the 12 bits of the S register kind of coming down here. And we need to basically combine that with our, so we've got our 10 bits because this is the addressable memory or the erasable memory. And then we need to generate the remaining bits in order to fully address our RAM. So here we go. We've got our 2 RAM chips that we're going to be using. And I'll just pull up the data sheet. Oops, it's the wrong one. Yep. So I'm going to be using a AS6C6264, which is a 8-bit or 8K by 8-bit, basically CMOS SRAM. You can kind of see we've got our pinout. So there's 13 address lines, and then we've got 8 data lines. Variety of chip enable inputs, write enable, output enable, power, ground, that sort of thing. So if we look at the actual circuitry, we can say, okay, so the first 10 bits of our S register correspond to the first 10 address bits of our RAM. And we're going to have 2 because each are 8 bits. So this is going to be our low 8 bits, and this is going to be our high 8 bits. And these are going to connect to the G register. Because I'm going to be implementing the parity check and the parity logic on my G board, I am going to actually send my G15, which is the parity line, over to the G register board. Now, the G register itself won't really see this because what happens is when you actually write into the G register, the contents of G16 is written into both G16 and G15. G15 is only used to calculate parity, and if there is a parity issue, it'll actually generate a alarm on the AGC, so it'll light up, and if you've seen some of the movies, that's when it'll start screaming at you, letting you know that there is a memory issue. Now, in order for the kind of the memory mapping or kind of the memory decoding to work, we also have to include our 3 EBANK bits to generate our complete address. Now, you may say, well, why don't I just bring those? I've got my 10 bits here. I've got my 3 bits, so 13 bits. Hey, we're great. We just have to basically bring everything across. However, it's not quite that simple. So if we look at the kind of the E addressing and address decoding, because of the way that some of the banks are used essentially is we're only swapping at there's a large kind of common memory that's used regardless of what bank that you're using. So we don't want to basically say, hey, these kind of low order bits are being switched out based on our which bank we're in. We only want to switch out the basically the kind of the basically the address range, which is this kind of 1400 to well, we've got we can see that what's switched out is 1400 to octal to 1777. So we can see that based on some of this logic is we're saying that if the S register contents fit into these kind of scenarios, we have it basically where we have these XXX, which is we don't care what the contents of our EBANK are. Basically, we can ignore them in all of these scenarios. Now that basically works out to say is okay, if bits that we only have to worry about kind of swapping in this kind of 1400 to 1407 or 1410 to 1423 is if the S register is either bit 9 is 1, bit 10 is 1, or we can see here, it's always like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There is these two scenarios here. We have 1, 0 and 0, 1, where we just don't care. But the only times basically is we want to make sure that we're including and generating kind of that composite address is if we're in basically the bits 9 and bits 10 are kind of in this combination. So basically, if bits 9 and 10 are both 1, then we want to basically pass along the contents of our EBANK register in order to generate the appropriate address. If that's not the case, then we can basically just ignore whatever is in the EBANK and just access it directly. If we don't do this, we could have a scenario where that there basically would be multiple versions of the kind of low memory for high bank. So you could have a scenario where this is 111, but then we're looking at some of these like low order addresses, which really we shouldn't be, right? There is no real 111, I think there's one or basically 0, 0, 0, 0, 0, 0, well, 1 here. So for example, if this Y was a 1, that would be address octal, I believe 0020, I believe. So if we basically said this address really doesn't exist because if we're actually looking at that kind of low order address, we should actually be accessing kind of this memory range, which basically doesn't care what the contents of the EBANK are. So in order to kind of replicate, or in order to do that, we've got these three input AND gates, which allow us to basically generate the appropriate address for our A10, A11, and A12. So our 11th, 12th, and 13th address bit. And basically we pull in the contents of bit 9 and bit 10 and combine them with the contents of our EBANK. And so basically if both S9 and S10 are 1s, we will then pass through the contents of the EBANK register. If these are not, then basically these will zero out. And so that means we're only going to basically swap in that bank of memory that we talked about in the last episode. So that kind of takes care of the address decoding. We get the right address that'll show up on our memory chips, and then we can kind of push the data out to or in from the G register. Now, in order to do that last part, we need a little bit of timing logic to determine when do we want to do a write enable, which is basically allow data to come in from the G register and write it into memory. Or we have our output, where we want to actually take contents from memory and push that out onto the G bus. Now, in the documentation, there actually is some erasable memory timing of basically when we normally read data from the erasable memory, which occurs during the T04 and T05 kind of pulse or kind of sequencing. So as we talked about, as we go through the sequence counter and we actually do the instruction decode, we kind of run through these kind of 12 kind of timing pulses in order to take our sub instruction and decode it into the specific control pulses that actually have to occur in order to make that sub instruction work. So based on that, we've got a timing. This is when we're actually reading data out of memory, which occurs at T4 and T5. And there's a little bit of an overlap, but we'll use T4 and T5 for our purposes. See if that causes an issue once we actually get this thing running. And then there's a write strobe, which is T11 and T12. Now you can see that there's like an REX read strobe and REY. So this is, because the Apollo guidance computer used that, erasable rope memory, it actually has to deal with a lot of its, basically the memory rewrite. So because a lot of RAM is, it's dynamic, right? So you have to actually continuously rewrite the memory or the contents of the memory into itself again and again and again and again in order to refresh the memory to prevent it basically from decaying away and losing the contents of the memory. And because the Apollo guidance computer, accesses that memory as a grid, it basically has a bunch of X control lines, a bunch of Y control lines, and between the two of them, it identifies which specific ring we're going to use to store or read that memory from, or that contents of that memory from. Now, because we're going to be using a IC, that SRAM chip that I talked about, that chip takes care of all that. Takes care of the refresh. It takes care of the decoding of the X lines versus the Y lines. So we don't have to worry about any of that circuitry. We just need to make sure that the timing is appropriate. So again, we've got T4 and T5 as to when we'll do our reads. And then we've got T11 and 12 when we'll do our writes. And when we look at that from a electronics perspective, we have our T4, T5, T11, T12. We AND that together, and then we invert it because it is negative logic. And we use that to determine when we're going to write data into the memory or read data out of the memory. Now you notice there's this extra line here, which basically comes from some of this, some logic that we had talked about earlier, which is basically there are certain scenarios where, because we're not really accessing memory, because we have those addressable registers, which are kind of like memory, but not, we basically want to say, hey, like in those scenarios, we don't actually want to write data into and out of RAM. And then there's also cases where we're going to be accessing fixed memory or ROM, where basically, depending on the address, we don't want to do anything to RAM, right? So if we're asking to read a certain address out of ROM, we don't want to actually read that data out of RAM at the same time. So this kind of prevents the two from occurring at the same time. We don't get any conflicts, and we're going to be basically making sure that the data that comes out onto our G bus or G register is clean. Now, just looking at just kind of simulating some of this logic here. First, I'll just kind of start kind of the select memory. So here we have, or sorry, the select logic. So here we have the write control as to like when do we actually want to write data into our EBANK. So we can basically, again, just set everything to 1, which in negative logic means that they're not asserted. So we've got kind of two scenarios. We can have our U2, which is our sum or adder to both banks. So once we do that, we assert our write, and that we want to be able to write data into our EBANK register. And then we also have, if we have our WSC, and then either the W3, our memory address 3 is selected, we'll write to it, or if memory 6, because that's our both bank, we'll also do it there. And then if neither, we won't write to it at all. On the right side, very, very similar. So we've got our, basically, we'll just say if we're not writing to anything, when our write timer comes by, we're not going to do anything at all. But if we have our RBBK control pulse asserted, we will assert this control pulse. So this is the one where we're actually going to write it to right lines right lines 1, 2, and 3. And then we have this scenario where, I mean, if if the address isn't what we need, we won't do anything. But if it's XB3, our memory address 3, we will, write it out. Or if it's XB6, realize I put W here, we will write it out. So that takes basically care of our EBANK service, so writing in and writing out. And then this is kind of like the decode logic that you can see up here, where if it's if bits 0 and or sorry S9 and 10 aren't set, it doesn't matter what's in our EBANK registers, we aren't going to pass anything out. But the moment if we say, hey, yeah, we do, we are in the S9 or S10, we will now, you can see, pass the contents of the EBANK register out to our memory address. And this down here is kind of our logic that we had talked about. So if we have a scenario where all of these are 0, which means that we're basically, in this case, we just got bit 1, so we're actually addressing, in this case, memory address 2. We basically will say, hey, disable access to erasable memory, because in this case, we actually want to be reading and writing data to the, and number 2, I believe, is the Q register. Let's just pull it up. Yes, the Q register. And that way, it again prevents us from trying to read or write into memory when we're actually trying to write into these registers. So it allows us to emulate that functionality that it looks like we're reading into a write or reading out of memory, but we're not. We're actually reading to or writing out of the, reading into or writing, writing into or reading out of those registers as if they were like memory, but not in this case. Okay, so that kind of takes care of the EBANK register. Next episode, we're going to talk about the FBANK, and then we'll start also getting into the SuperBank or F extended, the fixed extended bank. And again, Mike Stewart sent out some additional information because I was having some trouble finding like where are these bits set? Like, because it's pretty clear how we write data into the EBANK and the FBANK, but the fixed extended bank, I was having a harder time finding where exactly that data comes, and it actually comes from some of the I/O logic. So I've actually found the documentation in the manual itself where it shows, I think it's a I/O register 7 that brings in the contents of the extended register. But as I said, next episode we're going to cover the FBANK, and then the episode after that we'll cover the extended bank and kind of how that works, and that'll basically, with that, complete how we address memory in our guidance computer. And then we can start talking with the G register, which is that memory buffer and how data comes into and out of memory itself. That'll be fairly complicated because there's this whole concept of what they call editing control, where you can use the G register to do a bunch of kind of shift operations within that register itself. So again, that's going to get a little bit more complicated. As always, please subscribe so that you can know whenever another episode comes out. Like I said, I'm trying to do these about once a week as best I can. And as always, appreciate any feedback you have, any corrections. Always look forward to that interaction with people that are following along. Anyway, thank you very much, and we will see you next time.